Good. Can you hear me? Can you hear me?
Yes, you're fine. Yes.
Okay. Thank you very much, Bridget, for that kind introduction and also for the T-shirt. I'd like to thank the organizing committee giving me this opportunity to talk about this new liquid spectrometer that we've just commissioned and some of the early science. Just a second. It's okay. There we go. Brookhaven Laboratory was really the site of the world's first dedicated synchrotron. That was started in the mid 1980s, and I was sort of involved with building the first liquid spectrometer, second one in the world with Peter Pershan. First one was in Hamburg, and now it's the site of a third generation source. We were also the site of an SXSN conference. Last time it was in the States 6 years ago. So you can see that the NSLS2 ring is much larger than the previous NSLS ring, as shown in with the yellow ring. So just to tell you a little bit about the source, it's a third generation source, about 800 meters. It's 3 GeV. We're now at 400 milliamps, soon to be at 500 milliamps. We have a large energy range. Ability to have up to 60 ports. We don't have nearly that many yet. And first light goes back about 7 years ago. So I'm a part of a beamline, which is SMI. We're a station. There are two stations. There's a wide angle, small angle sort of beamline with a big vacuum chamber and the liquids instrument. So liquids actually have a very long history at Brookhaven. I mentioned I started in 1985 when I was actually a postdoc with Peter Pershan, and then I came down to Brookhaven soon thereafter, and we had a 30-year run. And there are many seminal papers from Brookhaven with Peter and Moshe Deutsch and Sunny Sinha, who are in the audience today. NSLS2 came along, and we put in a proposal to spearheaded for SMI. It was one of the second round of beamlines to be built. And part of that was having a liquids instrument in the front hutch. And the front hutch was, and this was going to include a double crystal deflector so the sample could stay fixed. And anyhow, the front hutch was built, but funds ran out and we had to move on. So in 2016, an idea, and Mark Schlossman was very involved, we wrote a proposal to build a canted undulator because it was canted ready. And this got great reviews, but nothing happened. But as part of this, we built the side station that was originally envisioned. And so that's come up over the last few years. People like Philip and Oleg have been very helpful. And part of this, building this instrument, involved using some old instrumentation from our old X22B instrument, as well as from an instrument at APS that we had built that's no longer there. So when we were told we could build this, we were told, well, it shouldn't just be for liquid instruments, it should be an open platform as well, something that could be used for, because we don't really have such capabilities at NSLS2. So this has to be shared, recycled parts, and we decided to go with a single deflector for various reasons, including a wall, which is pretty close. So our methods include standard methods for liquid surfaces over here, reflectivity, grazing angle fluorescence, GID, et cetera. We have the ability to put on Langmuir troughs, liquid metal chambers, small liquid chambers, and we have low vibration and the like. And also we have the ability to put on fairly large processing chambers. And as you'll see, there's a way to go about it by moving the deflector farther from the sample. And we have an energy range from 8 to 24 keV with about as much as 10 to the 12 photons per second. Of course, we'd like higher energy, but this is all this 3 GeV ring can really put out. So here I'm showing a rendering of the instrument. You'll see that there are two large granite blocks. The first one is housing the deflector, and the second one is housing the sample and the detector. And you'll notice that the first one with the deflector, it can move forward and back. We have to remove the flight path. That can be removed and varied, so we can actually vary the distance to the sample. And you'll note that this is a design where when the beam deflects downward, you have to move the sample up and down and sideways to so that you hit the sample, but that all geometry is all worked out and works perfectly. And you'll note that there's the ability to have 3 different detectors on the detector arm. I'll show you more in a little bit. Here's a picture of some of the people involved in the project with the granite tables before we started building up the instrument. So we actually tested the deflector now almost 2.5 years ago. We got the full instrument started about 2 years ago, but we really were interrupted and slowed down by COVID. And more recently, we have started user operations. So we've been running now for about 8 months. So here's the engineering design. As I said, we have many different recycled stages. Daniel Băsescu was the main engineer. He did a very nice job of putting this all together. And you can see the different, on the lower panel, you can see the different types of detectors that we have. We have one for X-ray reflectivity. We have a lambda detector with gallium arsenide, a SAX detector, which is 1.5 meters back, and we can put a wax detector up close. And as I mentioned, we can change the sample to crystal deflector distance by moving the crystal deflector to the right. Now, if you look at on the right, you'll see that this is a hutch where the beam must go through to reach the rear hutch, and we actually have to translate the instrument towards the door and rotate the instrument so that we can put the pipe in there. And we have to make damn sure that when the pipe is in there, we don't actually knock the instrument into it and sort of cause problems to the radiation, because having a leak, because when the rear hutch operates, it's also that pipe is part of the radiation protection. So for optics, we use a double crystal deflector upstream, silicon. Then we have mirrors. There are actually 3 mirrors. One for the horizontal, which focuses, 2 for the vertical, 1 focuses and 1 keeps the beam coming out level. These mirrors are actually bimorphs mirrors. And in the vertical, we like to focus at the sample because we're working at small angles and for various reasons to keep the beam a little bit larger, but also to maximize the reflection on the second crystal, we focus a little farther back. And you can see that we can see the spot size in the images on the bottom left. The bottom left one shows that the beam unfocused in the vertical. And then when we adjust the voltages on the bimorph, we can focus. And we've been able to focus as small as 31 microns. We should actually be able to focus smaller, but the bimorphs aren't perfect. They have imperfections. And there's also some vibrations. And we will solve this problems with CRLs, where we'll be able to put CRLs about 3 meters from the sample, and we should be able to focus to a few microns in the future. So it's a challenge to use old parts. So we're using this old Uber 3-circle or 4-circle over here, and we wanted to test how well when we tilt the beam downwards, because you have to rotate that big chi stage to tilt the beam downwards, how well that worked. So we used an angular interferometer, and you can see in the plot on the right, when we set a value of chi, we measure a value of chi, and there's an offset, and that offset can be as large as a few 10,000ths of a degree. Fortunately, we don't have to use the whole range. We only have to use the range in blue. And over that range, actually, the offset is fairly linear. And so it really doesn't really matter very much. In fact, if you fit the offset, you get a residual, and over much more than the range of interest, it's of the order of a millidegree. And so that certainly meets our specs. And that doesn't, of course, it would affect Q by a little bit, but that's a small error. But the fact is that we can track very well with this, as I'll demonstrate below. So certain things have to be made very compact. One of the trickier parts is the incident arm, where we have many components like an ion chamber, beam visualization, a diamond beam position monitor, a slit which is on axis. We can actually have a second monitor, an ion chamber, and an absorber bar. And we haven't fully instrumented it yet, but the diamond beam position monitor can be used to ascertain very quickly how well we're tracking. But we also know that from the monitor when we have small slits, and so it really hasn't been so necessary to use that. So one of the things how well these instruments track is how well the crystal deflection works, because as you rotate, you have to follow the Bragg reflection off a germanium 111 crystal. And you can see in this plot here with the rainbow colors that you have multiple curves. Those are phi rocking curves of the crystal, and you see that they change when you change alpha, and that's misaligned. But by very careful alignment, you can get all the rocking curves to happen at the same alpha. And we were able to do that by making both the chi and theta circles perpendicular to the beam. So that's really excellent. And then we look and see what the misalignment is. We look at the crystal tracking, which is within 2.2 millidegrees as we rotate. And that's really no adjustment, no geometry. So that's really, really good. And we can also see how well the height of the beam varies when we tilt the beam downward, and that's within a few microns as well. So we're very happy with the tracking of the instrument. So on the reflectivity arm, we actually use a gallium arsenide detector, which is 100 centimeters from the source. It's very nice because it works well at the high energies, has high count rate, and 55 micrometer pixels. So that's working nicely. So here's in an instrument like this, one of the first things you do, and I'm showing you some of the original data, is you measure water reflectivity. And you can see that on the left over a large dynamic range. The red curve is the red curve is on axis, and the black curve is off axis. And so you have the off axis. The on axis is what's measured in the yellow box, where you see that on the insert, and the off axis in the green and the red. And you can see how well there is some change in the monitor, but it's very smooth when you change. We have something here that actually adjusts the attenuator automatically, and you can see the attenuators coming in and out. And we've taken it water reflectivity many times, most recently just a month ago. And Guillaume Frichet, a scientist I've worked with, who's at SMI, has really helped with some of the software, and it's been a great pleasure to work with him. So we think we understand what the reflectivity from water is. This was worked out 35 years ago with Alan Braslow's paper, a classic paper, and the roughness, and that's how, measured by how the reflectivity deviates from the Fresnel reflectivity. And if you plot the R over RF in the bottom right versus Q squared, you get a straight line, and you get a roughness of about 3 angstroms. And yes, the same model of 35 years ago works today, so that's reassuring. So we can also do grazing incidence X-ray fluorescence. You can see the Vortex 90 detector. There's a sample chamber, and you notice there's a slot in the sample chamber, so we can put multiple samples, liquid samples, in this chamber. And actually, we can measure the surface pressure on multiple samples, and we can slide the sample chamber in and out, keeping the fluorescence detector fixed, and that helps us run with multiple samples. And you can see fluorescence data over here at various energies as a function of QZ. And you can see that above the critical angle of the water, you have much more fluorescence than below. And we believe, and we have some evidence that we can actually look at chloride fluorescence with this setup. So we're working on that. Here, for grazing incidence diffraction, we have our detector. We thought we were going to use the detector at a 0.5 meter position. It's sort of shown over here. It's now just using for electronics, but we're actually putting a detector 1.5 meters back. This was done originally. This is a rod scan for a monolayer on water, and it was very preliminary stuff in the early days. Now we're using a Pilatus 300K at this detector position. You'll notice that the background has this weird shape here. I tried to be clever and added a little snout up here with this aperture, and we're seeing shielding. So it's actually better to remove. You shouldn't work too hard to remove the background because unless you can do it everywhere. The main point of this is that we can actually, these rods this is taken in one shot. And the fact that the detector is farther back actually works very nicely, because what it allows you to do is you get fairly good resolution without having to use a slit in the front and to scan, or without using solar slits. Eventually, we're going to replace this 300K with a 1M. And what I want to show you over here is that we really want to get out to about 1 inverse angstroms. This is from an old paper of someone else of sort of data of a monolayer that you want to get this far up. And what I want to show you over here is that if you want to get to this 1 inverse angstroms at 16 kV, that if you use this 1M detector, you can get this large range in reciprocal space without having to piece it together, and you get it very fast. So that's very nice. So let me give you a few examples of some data from users. First, I'm going to show you some gold nanoparticle work. This is from David Vaknin's group. They started early on. These gold nanoparticles are grafted with a water-soluble polymer called PEG, and they vary the chain length. So the chain length here, for instance, could be, we're varying the chain length here from 2K molecular weight, for instance, to 40K molecular weight over here. And we're trying to understand how the structure depends on the molecular weight, because these are grafted on and how they absorb water. So we can add things like, what's that?
3 minutes.
Okay, so we can add electrolytes over here, so you can see reflectivity data, grazing incidence data, and we can measure how this varies.
Sorry, that was a mistake. It should be 12 minutes. I misread the clock. You have 12 minutes. Everything's.
Thank you. Okay, so anyhow, I think the basic story is over here, that we can measure reflectivity. We can do analysis and see what the density profile is over here. You can see this type of, this is a hexagonal structure over here. And these are, we're varying the molecular weight, and we can see how the peak positions vary with molecular weight. And from this, we can get distances, and we can see how the distances vary with molecular weight. And this follows a power law, and we don't fully understand it. We have a little more data, but we're trying to understand better why it follows exactly this behavior with this slope. So one of the interesting things is now if you mix different nanoparticles in solutions, you can find very interesting binary superlattices. We have multiple examples. I'm just going to show you one. So what we do is we're mixing in solution one with a 5 nanometer nanoparticle with a 5K PEG and a 10 nanometer with a 2K. And you can look at the diffraction pattern of each of them over here. And you can look at the diffraction where you mix both of them together. And one of the things is there's a new peak here. That's from a superlattice peak over here. But the other thing that I'll show you something about this, but the fundamental over here, if you look here, has a peak of maybe about 0.28, and that sort of shows the same fundamental as this one over here. So predominantly the structure has to be built up of these 10 nanoparticles with the 10K, where it also has some of the smaller ones as well. So if you look at the diffraction, and you can fit the data nicely with this AB2 structure, which has 3 nanoparticles per unit cell, it forms a √3 by √3 structure, and that fits the data. That explains the data over here. All the peaks we see over here are again associated with a hexagonal arrangement. And again, we know that it's this √3 by √3. Another possibility would be a 2 by 2 type of structure that would give rise to other diffraction peaks that we don't observe. So another problem that we've looked at with Honghu Zhang, who's a postdoc with Oleg Gong, had actually been with David Vaknin before, is instead of using PEG, we're using peptoids over here. These peptoids are kind of interesting because they have bioinertness as well. They're actually they coating thinner than the PEG, and you can have sequence-defined properties. And the thickness of this is only about 1.5 nanometers, and the nanoparticle is 10 nanometers. So you can see we can get beautiful reflectivity data. You can see the contrast is changing depending on what the underlying solution is. With water or sodium chloride, you get much less contrast. But if you add this buffer, phosphate buffer, you can see you get much better contrast. And what that's telling you is that you're getting much higher coverage by the addition of the phosphate buffer. So if you also do grazing incidence scattering, you can see we get beautiful data over here. You can see that it's much more ordered over here. The peaks are sharper. This is the sharpest when you have the phosphate buffer and the sodium chloride. Just sodium chloride or just phosphate buffer, it's not nearly as sharp. So both of them are important to doing this. And one of the reasons we're interested in doing this is we want to see if you can get ordered superlattices that are more compact than the PEG. And these are much more compact because of the thinner shell. And more compact layers are important because it can improve the plasmatic coupling. I'm going to switch topics over here. This is a liquid, but it's you'll see it's not really at the vapor interface. This is a molten salt. I'm the PI on this project. Molten salts are lithium chloride, potassium chloride. They're very relevant to nuclear reactors, batteries, solar, high temperature solar installations. You have to get to high temperature. Like aqueous, there's no double layer here. The interfacial behavior in terms of corrosion is very important for these types of applications and poorly understood. So what type of arrangement? This is a figure from ionic liquids. You could get a layering of the various cations and anions, or you could get a checkerboard arrangement, but we don't know how these are arranged. So the first idea was to look at this as a vapor interface, but if you look, because we had looked at similar things in type of layering in liquid metals, the surface tension is much higher, 500 to 700 for mercury and gallium. But for these salts, it's much lower and much higher temperatures. So you have to worry about the capillary roughness, that is how the fluctuation of the surface is at the surface, and that limits your resolving power in real space. And if you work it out for the vapor interface, this capillary roughness is too large because of these surface tension regions, and the maximum Q you can really get to is 0.7 inverse angstroms, but you really want to get to 1.5 inverse angstroms if you want to look at layering. I'll show you that in a little bit. So then we got the idea, well, we'll look at it as a solid interface. We know we can get solids very flat. You don't have capillary roughness. Substrates like diamond and sapphire are very good, but you need high energy X-rays. I'll show you, we haven't published any experimental work, but there is part of where we did MD simulations, and you can see, for instance, rubidium chloride, you can see that there's layering type of here, and these are actually shown at different potentials, which one can do. And so this is in real space and reciprocal space. You can see these, the effects of potential, and you can see peaks here in the reflectivity, but you have to get to fairly large Q. So this is quite challenging. So how do you go about doing the experiment? Well, as I showed you before, you think you would go through the molten salt and then bounce off the solid and reflect and measure it over here. It turns out that it's actually much preferred to go through the solid interface and come this way, because the molten salt actually has more absorption than the substrate. It has materials with higher Z, and you want to vary those components. So that won't change when you come through the solid. And so at the type of energies we're at 24 kV, you can go through about 2 millimeters of sapphire, much more if you have diamond. We're working with sapphire now. We have diamond arriving actually next week. So we picked 5 millimeters to go through, and we have a setup to do that. We're actually running at 23 kV. Of course, like I'm envious of all the people who can run at 70 kV. We hope to do that sometime in Europe or at the APS. So one of the things is you have to worry about the index of refraction. If you come this way, you have a critical angle. If you come this way, you don't have a critical angle. So here I'm showing what you would have coming from the top with a critical angle, coming the other way, you don't have a critical angle. And it turns out if you calculate the reflectivity, this same formula that we always use works. Normally this coefficient A is positive. If you come through the other way, it's negative. And that's really just because the index of refraction changed. The sign of the index of refraction is opposite going the other way. But the important thing is what really matters that large Q, it doesn't really matter whether you have a critical angle or not. The data looks the same. So here, I just want to show you, here's our sample cell over here where it's opened in early stages. There's a tilt stage underneath because, and we tilt the sample rather than tilt the beam downward. And what's really, here's a schematic representation. It's quite small. We made a U-shaped shell out of quartz, cell out of quartz. We were able to put on quarter millimeter quartz windows by heating at high temperature and getting them to fuse together. That's showing the quartz over here with the sample underneath and some molten salt on top of it. So this is quite a challenging experiment. So we've only recently have been able to do demonstration experiments, and I'll just show you a little bit. Here's just normal reflectivity off the sapphire and air. You'll notice this dip because there's some sort of organic contamination, and R over RF. This is typically what you see when you have an organic film. Here it's 15 angstroms thick. So we also went to higher energy where we have all this attenuation going through the sample. You can see again this characteristic dip coming from the organic layer coming the other way. It's not exactly the same sample, but it shows very similar to what's over on the left. And the last experiment I want to show you, which happened in the last hour of beam time in October, is coming through the sapphire with the molten salt. And we were actually able to get some data. This is R over RF. I don't understand why it came up like this. I don't understand the shape. We have to do better. But the point is that this whole setup works here. So I think this opens up the possibility of looking at surface-induced layering at molten salts. Just very quickly, we have a Quiberon trough, which we're going to be installing, and Chen at Daisy was very helpful. They have a similar trough. And one of the unique designs here is that the cover just lifts off. All the connections are underneath, so it's very easy to get access to everything. So just to end this in the last slide, we've had 12 proposals submitted. 6 have had beam time. We're already oversubscribed by a factor of 2. When the APS shuts down for their upgrade in a little over a year, we'll be the only liquid instrument in the US. I don't know. We're only running about 25% of the time because the other station runs. So I don't know how we're going to absorb so many users. We really have to increase the efficiency with multiple cells with pressure measurements. And it's difficult. I'm the only scientist on the beamline. So these the good news is the measurements are fast. Reflectivity takes about 20 minutes, the GID only a few minutes. And we really want to be able to do liquids in the future, but that's going to require CRLs. So thank you for your attention, and thank you, Bridget.